So if anybody, does anybody have a preference on 11 or 12? 12? Sure. So we have r is equal to negative 2 plus 3t I plus 6 minus 7 tj plus 4 plus tk. And it just asks to find 3 points on the line. So to do this, all I'm going to do is I'm just going to pick some values for t. Each value of t that I pick is going to correspond to a point. So I'll just start maybe with t equals 0. So if I do that, this turns into negative 2i plus 6j plus 4k. Is everybody okay with how I got that? We're just all the t's zeroed out. And remember that this is equivalent to the component form vector negative 2, 6, 4, because the I is just the x component, the j is the y component, and the k is the z component, which is just really the same thing as the point negative 2, 6, 4. And I can continue doing this kind of as much as as many times as I'd like for whatever values of t that I please. So I would pick values of t that are convenient to work with. So maybe let's do t equals 1. So that's going to give us 1i plus negative 1j plus 5k, which then is going to turn into the point 1, negative 1, 5. Everybody okay there? And you don't have to pick just negative or positives. You could pick negatives. So just for the sake of argument, maybe we pick negative 1. You could pick 2. You could pick 15. You could pick 175. You could pick 1.6. Any value of t is fine. So if I do that, let's see, I'd have negative 5i plus, what's that, 13j plus 3k. So I'd have the point negative 5, 13, 3. Jackie, does that feel okay?
Yes.
So just pick whatever values of t you want. And it'll evaluate down to 3 components, and those 3 components are just then your points. Okay? So not too bad, right? All right. Who else had questions from this? Are there other things from this sheet that we would like to talk about? Jackie again?
Sorry.
You don't have to apologize for asking questions.
Can you do one of the graphing ones?
Yeah, does anyone have a preference on 1 through 4?
2, 4? Yeah, 3 or 4 please.
Okay. Well, 3's kind of trivial, so let's do 4. Is that okay with you guys? Okay. So I'm going to start by drawing in 3 tick marks on the negative side of the x-axis. So that's the part going like backward into the board. So that's there. I'm going to draw 6 tick marks on the positive y-axis. So that's there. And then 4 tick marks on the negative z-axis, which is there. And remember, this is x, y, and z axes. Okay. So what I'm going to do is I'm going to start by finding that last tick mark on the x-axis. And I'm just going to draw a line that's parallel to the y-axis. And then I'm going to find the last tick mark on the y-axis. and draw a line that's parallel to the x-axis. What that's going to do then is it creates like either the top or the bottom of my box that I'm going to draw. So I have like 4 corners for my box, right? Now, if I'm graphing in 2 dimensions, the point that I care about is here, right? That's the one where I went -3 in the x direction and 6 in the y direction. Is that point there? Everybody agree on that? Okay. So what I'm going to do now is I'm going to now project this graph into 3 dimensions. So I'm going to start with the point at the origin, and I'm going to go down 4 units on the z-axis. I'm going to find the other point on the y-axis and just go down 4 units. And then I'm going to go to the other 2 points on my square and just estimate down 4 units. Everybody okay there? So notice the point in red was the one that I said was the part of the graph in 2 dimensions. Whatever point that point, or wherever that point gets projected to then, is what I care about in 3 dimensions. But this was graphing a vector, is what we're actually supposed to be doing in this problem. So to graph the vector, all I do is I go from the origin, to that point that I just drew. So there's my vector. Is that okay, Jackie?
When you draw the vector, how do I need to?
So you're going from, in this case, the point 0, 0, 0 to the point -3, 6, -4. So again, to figure that out, I'm going to go from, this is the point -3, 6. So when I project that down, it's going to be the one that's kind of attached to it in the z direction. Does that make sense? Okay. Ben?
So is number 3 just a square?
Right, yes. It's really just a 2-dimensional problem
Yeah, right.
since the x component is 0.
Yeah.
So that one should have been pretty easy because there is no box really. It's just a 2-dimensional problem really.
Yeah.
Okay. Good questions, guys. Or is there anything else from this sheet that we need to talk about, Sydney?
Number 7.
7? Sure. So there's lots of different ways we could answer this question. Remember that writing a vector equation for the line, there's not one unique answer to this. There's like an infinite variety of answers that would be acceptable. So we're given that we need to pass through, 2 points. Those 2 points are these. I'm going to call this one A and this one B, just for the sake of argument. So my vector equation for a line is this. So for my R naught, this is the point vector. The obvious choices for R naught would be, thank you,
Yeah.
one of these 2. It doesn't really matter which one. For the sake of writing an answer down, let's use that one. And then for V, the direction vector, I'm either going to do AB or I could do BA, are the 2 obvious choices. Okay. So again, just for the sake of argument, let's do this one. So AB is going to be the points from point B, and then subtracting from them the points from point A. Okay with that? So now all I have to do is put this together. So R is equal to R naught plus V T. Yep. So there's, like 4 different possibilities that you could have written your answer as, depending on like whether you used which point you used and whether you used vector A or vector AB or vector BA. So there's lots of different options there. It doesn't really matter which one you choose. They're all equivalent. Does that feel okay there? And again, not super difficult, the procedure, right? Just kind of knowing how to do it is the issue, but the actual what if you're doing is not really difficult, right? I mean, you had to do a little bit of subtraction and put something in a formula. It wasn't too bad. Ben?
Lots of things here.
Well, I mean, there's other points on this line other than these 2 that you're given. Like you could find another point and use that one, and you could use that other point to create another direction. So there's like infinite number of representations. Now, realistically, with the information that you're given, you wouldn't do any of those things. You'd have one of these 4 choices, but it doesn't mean you can't. But yeah, from a realistic standpoint, you wouldn't do any of those things. Brockton.
Did you write that answer in your
Sure. So to do that, this is the I components. So I do that. And then this is the J components. And then the last one is the K component. Does that feel okay there, Brockton? So again, like not difficult to translate one to the other. You just have to be able to like remember what those things mean, right? So like the definitions really matter a lot, that the I is just, we're talking about the X component of our vectors. So you just take all the X components together and you put them in a parenthesis and stick the I at the end. The thing you have to remember about is like making sure you put the T's on because this vector has a T scalar multiplied to it. But not difficult to do that. Okay. Anyone else? I think we went through just about a little bit of everything there, right? Okay. So let's.
Can we do 13 or 14?
Oh, sure. Do you have a preference?
I don't know how to do either one. So.
They're really the same problem. All right. So, does anybody have a preference? Oh, sure. I just like when somebody asks me this one or this one, it's like, okay, so you don't have a preference. Does anyone else really prefer one over the other? So it just kind of eliminates a question. So we want to find out if this point 5, 8, 12 lies on this line here R. So all I'm going to do to solve this is I'm going to see if I can find one value of t that's going to make the x be 5, the y be 8, and the z be 12. So that value of t has to be the same value to get all three of those components. So for the x's, I'm going to say that 5 has to equal -4 plus -3t. And then for the y's, we're going to say that 8 has to equal 22 plus 5t. And then for the last one, 12 has to equal 9 plus -1t. And so now all I need to do is solve for t. So here I'll add 4 to both sides and divide by -3. When I do that, I get -3. Here I'm going to subtract 22 from both sides and divide by 5. That gives me -14 over 5. And right now I could stop because these t's don't agree. I would need a different t to get the x coordinate 5 and a different t to get the y coordinate to be 8. So there's not one t that's going to give me both those x and y coordinates together. So that point can't possibly lie on this line, right? So I could stop right here. Since those t values are different, I'm done. Now, if they were still the same, I'd have to go and find the third one. And if it was the same also, then yes, we're good. But you have to have all of the t's be the same, or that point can't lie on the line. Everybody okay with that? And as soon as you see two t's that disagree, you can stop. You don't need to find the third one, although it's not saving, not saving a whole lot of work. I think that comes out to be -3 also, just FYI. Bella, does that feel okay there?
Yeah, I think.
Okay.
For number 14, if we were to do that one, I just don't understand how to convert it from the linear combination back to the...
You don't need to.
Oh, okay.
In fact, I would encourage you not to because it just kind of wastes a little bit of time.
Oh.
So the x component is going to come from 15 minus 4t.
Okay.
And that has to equal the x.
Oh.
And then the y comes from the j's. And then the k or the z comes from the k's. And so right there, that's good, right? 12 equals 12 is always true. So I don't actually have a t value there for the last one, but that's okay. If you don't have a t to solve for it, but it equals what it's supposed to equal, it's fine. So we just really have to worry about those other two. I think this one works out. At a quick glance, I think you get 5 over 2 for both of them. Does that feel okay?
Yeah, thank you.
Yeah, so again, you could convert it back into the other form, which is fine, but you don't really need to. Like the linear combination form is honestly even a little easier to do this kind of thing with because you already have the part that gives you the x is already grouped together. You know what I mean? Okay. So let's move on here today. We're going to talk some today about planes. Hi, Grace. Thank you. David, come on down. You're the next contestant on Who's Leaving School Early. You're welcome.
Dude.
Yeah, but you have to do the rest of the math to figure that out. Yeah, if there they're all the same fraction.
All right. So in 2 dimensions, we talk about graphing lines. In 3 dimensions, we can talk still about graphing lines, but there's another geometric object that we can graph in 3 dimensions, and that's a plane. So in 2 dimensions, remember we had the standard form equation for a line. Oops. You guys kind of remember that equation from your algebra or geometry course in the past, right? In 3 dimensions, we have an equation for a plane. We call this the Cartesian form, is the vocab that I'm going to use here. But it just basically is talking, Cartesian is just referencing the x, y, z in the case of a plane coordinate system. So it basically just means you're having x's and y's in our formula. And in both of these cases, we write the a, b, c, and d as integers. So an example of a plane, or the equation of a plane, I guess I should say, is something like this. 2x plus 6y plus 3z is equal to 12. Now, if we wanted to graph something like this, the easiest way to do that is to change the equation a little bit. My goal to change the equation is going to be to have it equal to 1. So to do that, I'm just going to divide both sides by 12. Everybody okay with that plan? If I divide both sides by 12, I get x over 6 plus y over 2 plus z over 4 is equal to 1. Is everybody okay with how I got these fractions here? Two over 12 reduces to 1/6. 6 over 12 reduces to 1/2. 3 over 12 reduces to 1/4. Is everybody okay there? Okay. So what I'm going to do now is I'm going to generate 3 points that lie on this plane. And I'm going to do this in the easiest way possible. So 1 point could be 6, 0, 0. Since 6 over 6 is 1, and 0 over any non-zero number is just 0, 1 plus 0 plus 0 gives us 1, so that satisfies our equation, right? Okay. Now let's pick the y-coordinate to be 1. What value of y is going to make the y-coordinate 1? 2. And since the y-coordinate is now 1, the x's and z's have to be 0 to satisfy the equation. Is that okay? And then anybody with a guess as to what my third point would be? 0, 0, 4. Very good. Is everybody okay there? Okay. So to graph this then, 1, 2, 3, 4, 5, 6, and there's a point. And then 1, 2, there's a point. And 1, 2, 3, 4, and there's a point. So to do this, to graph this now, I'm just going to connect those 3 points. And if I kind of shade that, that's the plane that we've kind of drawn. Is everybody okay with that idea? Okay. Okay. So what we want to talk about now is the vector equation for a plane. So the formula for this So our vector equation for a plane is r equals m plus as plus bt, where m is a point vector, so m is just some point in the plane. S and t are direction vectors, so their origin or their initial point needs to be the point to m. And they also have to lie inside of that plane. And a and b are just our parameters, so they're real numbers, just like the t was in the equation for a line. So as a very trivial example, if I know that we have a point in the plane and I know that these two vectors also lie in the plane, then we can just say our equation for the plane is that. Is everybody okay with that? So once we have a point in the plane and two vectors in the plane, we just can plug them into the formula. The two vectors, there doesn't really need to be anything special about them. They just have to lie in the plane. So we could be a little bit less specific here, and instead of giving you a point and a vector, and the two vectors that lie in the plane, we could just give you 3 points. If you remember back to geometry, and this would have been a long time ago because it was like in the first semester, one of your axioms for geometry is that 3 points define a plane, just like any 2 points define a line. Everybody kind of maybe remember that? So as long as you have 3 points, that defines a plane. So to write my equation for a plane, I'm going to do m plus as plus bt. So my vector m could be any of these 3. Doesn't matter which one you choose. For the sake of the argument, let's choose this one. Yes, Michael? Of course. Is everybody okay with that? And for the sake of notation, I'm just going to refer to these points as A, B, and C. So my vector S and T could be AB or BA, could be BC or CB, or it could be AC or CA. Now it matters a little bit which of these you choose. You can't use AB and also BA. You have to use, for example, let's do AB and BC for the sake of this example. Actually, I take that back. Let's do AC. You just need to involve all 3 points. So you can't use AB and BA, for example, because you haven't used all 3 of the points. But it doesn't really matter which 3, whether you do AB or BA, or you could have done BC instead of AC, it doesn't, you have a lot of choice there, but you can't just any 2 won't do, right? Okay. So AB is going to be point B minus point A and then AC is going to be point C minus point A Everybody okay there? So if I put this all together then, I have 3, 4, -1 plus 2, -10, 2 times A plus 2, -3, -7 times B. Does everybody feel okay on that? So very similar to when we wrote the vector equation for a line, right? Very similar procedure. Nothing terribly complicated. All we had to do was a little bit of subtraction, but knowing how to do this, how to manipulate these 3 points is the tricky part. The actual manipulation is pretty easy, right? All we had to do was a little bit of subtraction, put some stuff in the formula. Let's then ask, say, given a equation for a plane, maybe we ask if this point lies on the plane. Okay, so we're going to find out if this point lies on this plane. So the equation that I'm going to set up then is going to be 5 equals 8 plus 2a plus 1b. Does everybody see how I get that, or how I got this equation? I took the x, 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 all the way across, right? What's the next equation I would want? Great. And then my last equation then would be 3 equals 3 plus 1a minus 3b. Notice in each of these equations I have 2 variables, right? In order to solve an equation with 2 variables, I have to create a system of equations and then solve that system. So we're going to use a matrix here to solve this. Now, to solve a 2-variable system, how many equations do I need? 2. How many do I have? I have 3, right? So I'm just going to pick any of these 2. It doesn't matter. I'm going to pick the first 2 to form my system. So I'm going to do a little bit of rearranging so that I'm going to write down my system the same way I would type it into my calculator. So 2a plus b. And then I'm going to subtract the 8 over to the other side. And then I have negative 1a plus 1b. And I'm going to subtract the 1 to the other side. So this is the system that I'm going to solve in my calculator. So I'm going to do the row reduced echelon form for 2, 1, negative 3, negative 1, 1, negative 2. So let's type that in. Have I gone too fast? Or is there some questions? We okay? Please stop me if if I buzz through something that you're not sure about, or if you think I made a mistake, or any of those sorts of things. Okay. So I've gone ahead and entered my matrix into my calculator. Once I've done that, I'm going to exit out. Then go back into the matrix menu, but this time go over to the math tab, go down to the bottom and find the RREF command, and then perform that on matrix A that I just made. So I get some crazy decimals, but if you just do the fraction command on top of your matrix, it'll give you fractions, which is usually better than what we had before. Is everybody okay there? So what this tells me then is my solution for A is negative 1/3, And my solution for B is negative 7/3.
So Mr. Cook, you could pick any two of those.
Yes, but we still have one little thing left to do here.
Okay.
We still have one little thing left to do. So this value for A and B satisfies these two equations, right? That's what we just proved. Do we know that they satisfy the third equation? No. So we need to check that still. Okay. So if I do that, 3, well, plus 3 plus negative 1/3, and that just turns into plus 7. Is that true? No, right? So we would say that this guy does not lie on our line, or on our plane. So we got to make sure that we're being careful there. If it did satisfy the equation, then the answer would be yes. So you have to make sure the values of A and B that you've solved for satisfy all three equations. We know they satisfy two, the two that we solved the system for, but we don't know that they satisfy the third one. We have to go back and check that. Yes.
You say again what menu you want to do that?
So back to the matrix menu, and then over to the math tab.
Oh.
And then it's down near the bottom. Okay? Okay. Is everybody okay with this problem? So it's a little bit involved. You have to solve a system, but it's not so much, right? Coming up with the system of equations is pretty quick. Solving a system on your calculator is pretty quick. So let's talk next about converting between Cartesian and vector form. So we'll start with the easy direction. It's quite easy to convert from Cartesian form to vector form. So for example, let's say that we have the Cartesian equation of a plane. (2x minus 3y plus 8z is equal to 24. All I'm going to do here is I'm going to find 3 points on this plane and then use those 3 points to write the vector equation, just like we did previously. So in order to find 3 points on this plane, I'm going to start by making this equation equal to 1. So I'll divide both sides by 24. Oops. Everybody okay there? So very quickly, I've got 3 points. And then to write my vector equation for a plane, I use this equation where m is going to be, I'll just use the first point for m. S, I'm going to just do the first point minus the second point. And for vector t, I'll do the first point minus the third point. And I'm done. I just need to rewrite it in the proper form now. And that's it. Is everybody okay there? Okay. Worth noting that this process could get a little messier if, say, this number doesn't divide, isn't divisible by each of the coefficients, then you're going to get some fractions rolling around in there, but it's not the end of the world. Okay? It gets a little messy with some fractions, but you don't really have to do that much with them other than like subtract some fractions potentially, which is not the end of the world. Okay? But just as a heads up, that could get a little yucky, but not terribly yucky. All right. Let's talk now about the more difficult direction, and that's going from vector form to Cartesian. And I'm just going to start with an example. So let's say we have this vector equation for the plane. Okay. I'm going to start a similar way to what I did in the previous problem, and I'm going to find 3 points that lie in this plane using this equation. To do that, I'm going to pick values for A and B, and then use those to generate the points. So the first point I'm going to find, I'm just going to pick A to be 0 and B to be 0. Again, I'm just picking things that are going to give me, or that'll be convenient to work with. Doesn't really matter the values you pick for A or B. You can pick any values for either one, and they can be different, which we'll do in a moment. But 0 and 0 really make this pretty trivial, right? Because everything drops off other than that first vector. So that's just one of our points. Next thing I'll do is I'll pick A to be 1 and B to be 0. So when I do that, I'm basically just adding these two vectors together. Everybody's okay there? And then to get my third point, I'm going to pick A to be 1, or A to be 0 and B to be 1. So I'd just be like adding those two vectors there. Is everybody okay there? Okay. So this is what I need. The problem here arises that if you remember the Cartesian form, oops, is ax plus by plus cz is equal to d. Right? How many variables do I have there? 4. So to be able to deal with this, I have four things that I need, 4 parameters, a, b, c, and d. But I'm only going to be able to create equations with like 3 inputs, x, y, and z. So I need to figure out a way to reduce out one of these 3 variables. Well, what did we do to graph an equation for a plane? We divided by d to make the right-hand side 1. So I'm going to do that same thing here. And I'm going to rename a over d as just a, b over d as just b, and c over d as just c. I used the lower cases there to kind of differentiate. But remember, a, b, c, and d are all integers. So by doing a divided by d, all I'm getting is a fraction. So I'm just going to call that fraction little a. Is that okay with everybody? Yeah, so I just created a new name for it. Now I have an equation with just 3 variables in it. Right? And we're going to do this same process every single time, so don't really need to write this out. But I want to explain to you what equations we're using and how we're generating this system, because I think that helps make what we're about to do a little bit easier. But all I'm going to do now is I'm going to take our 3 points and plug the values for x, y, and z into this equation. So the first point was 3, 2, 1. So I have 3x plus 2y plus 1z equal to 1. My second point was 4, 7, negative 1. So I have 4x plus 7y minus 1z equals 1. And my last point was 0, 7, 2. So I have 0x plus 7y plus 2z is equal to 1. Do I really need to write the 0x there? I mean, not really. I just do it because I'm not really going to work with this system. I'm just going to turn it into a matrix to solve now. So just like we've done before, we're going to do RREF on this matrix. Is everybody okay there, Ben?
Why don't we do it to like read the last problem?
So in the last problem, we had a and b. We had only 2 variables, so we only need 2 equations. Here we have 3 variables, so we need 3 equations. So it's just a matter of how many parameters we're trying to solve for. Is that cool? Okay. And so the last thing I'm going to do is I'm going to go and enter this in to my calculator. So I have 3 rows and 4 columns. So 3, 2, 1, 1, 4, 7, negative 1, 1, and then 0, 7, 2, 1. So that's all entered in. Now I'm just going to go back in, find my math tab, RREF on this matrix we just made. And again, I got decimals, which I don't love, so I'm going to just do the fraction command on that. So 1/5, 1/15, and 4/15. So this tells me little a is 1/5, little b is 1/15, and little c is 4/15. Or in other words, I have 1/5 times x plus 1/15 times y plus 4/15 times z is equal to 1. This is me just plugging this back in, my answers for a, b, and c into that equation. And my last step now is going to be to clear fractions. So what do I need to multiply both sides of this equation by to get rid of all of these fractions? 15, right? So when I do that, 15 times 1/5 is 3, so I have 3x. 15 times 1/15 is just 1. 15 times 4/15 is just 4. So here is my Cartesian form equation for the plane. This is where we're going to stop for today.